For years, everything looked normal. Hikers walked its trails. Families camped in its shadow, snapping photos against a horizon that never seemed to change. Snow fell every winter and melted every summer, like clockwork, the way it always had. Nothing about Mount Rainier seemed different, but deep underground, something had started to move. Not an explosion, not lava, not even a tremor you could feel standing on the surface. Just a lift, a few millimeters, then a few more. Satellites caught it first, sweeping over the mountain again and again, comparing one pass to the next. Then GPS stations, bolted directly into solid bedrock, accurate to within millimeters, confirmed what the satellites suspected. The mountain was rising. And when a volcano like this one starts rising, scientists don't panic, but they stop everything else, and they pay very close attention. Because sometimes, this is exactly how the story begins. So here's the question everyone wants answered right now. Is magma pushing toward the surface at this very moment? Is Rainier waking up after generations of silence? Or is this something else entirely? Something scientists have documented before? Something that has happened and quietly resolved itself more than once, without anyone even noticing? Stick with me, because by the end of this video, you'll understand exactly what's happening beneath one of the most dangerous volcanoes in North America. What the data actually shows, what history says about mountains like this one, and why the honest answer is far more complicated than a simple yes or no. Let's start with where we actually are, geologically speaking. The Pacific Northwest sits directly on top of a slow-motion collision that has been happening for millions of years. Far beneath the Pacific Ocean, a slab of oceanic crust called the Juan de Fuca Plate is sliding underneath the North American continent, just a few centimeters a year, slower than your fingernails grow. That collision, repeated over millions of years, built the entire Cascade volcanic arc: Mount St. Helens, Mount Hood, Mount Shasta, Lassen Peak, and Mount Rainier, the tallest, the most heavily glaciated, and arguably the most closely watched volcano in the continental United States. Rainier isn't just tall, it's dangerous in a very specific way. More than 80,000 people currently live on top of old volcanic mudflows from this exact mountain. Solidified rivers of rock, ash, and debris from eruptions that happened centuries ago. And here's the part that keeps volcanologists up at night. Rainier is covered in 26 active glaciers, more ice than any other volcano in the lower 48 states. If this mountain erupts, the lava itself might not be the biggest danger. It's what happens when intense heat meets that much ice and snow all at once. Sudden melting, sending massive flows of mud, rock, and debris, known as lahars, roaring down river valleys at speeds that leave almost no time to escape. So when the ground starts moving here, it isn't a passing curiosity for a few scientists in a lab. It becomes a 5-alarm priority for an entire monitoring network. Now, here's what most people get wrong about volcanoes in general. They picture a mountain as one solid piece of rock, sitting quietly until the day it explodes. In reality, a volcano is more like the lid on top of an enormous, chaotic underground plumbing system. Networks of fractures, pockets of gas, superheated water, and pools of molten or partially molten rock, all constantly shifting, constantly changing pressure. Most of the time, none of that activity ever reaches the surface. The volcano just breathes, quietly, for years, sometimes for decades at a stretch, with nothing visible happening at all. That underground breathing is what scientists call inflation. Picture a balloon slowly inflating underneath a thick blanket. The blanket doesn't suddenly burst open. It doesn't rip or tear. It just rises, smoothly, gradually, almost imperceptibly. No cracks appear, no steam bursts out. Just a landscape getting very slightly, very slowly, taller. Detecting a change that small requires some of the most sensitive instruments ever built. The GPS stations planted around Rainier don't just measure position to the nearest meter, or even the nearest centimeter. They calculate their exact location relative to satellites in orbit, continuously, every single second, with a precision measured in millimeters. If the mountain shifts even slightly, the instruments know almost immediately. Then there's a second technology, arguably even more powerful. InSAR, short for Interferometric Synthetic Aperture Radar. Radar satellites scan the same stretch of ground weeks or months apart. Then compare the signals that bounce back. If the surface has moved even a tiny amount in between, the difference shows up as vivid color patterns spreading across the entire mountain. An image that looks almost like a heat map, except it's mapping motion instead of temperature. Scientists have a phrase for this. They call it watching the Earth breathe from space. And recently, both systems, the ground stations and the satellites, agreed with each other. The surface around Rainier wasn't holding steady, it was rising. Now, before your mind jumps straight to worst-case scenarios, here's the part that most dramatic headlines conveniently leave out. Inflation does not automatically mean eruption. Many volcanoes around the world inflate, then deflate, then inflate again, cycling for years or even decades without ever producing a single drop of lava. Pressure builds underground. Pressure gets released, often slowly and harmlessly. The system resets itself, and Rainier specifically has inflated before in its recorded history and simply gone quiet again afterward. So ground uplift all by itself doesn't answer the big question. It only confirms that something underground has changed. The real investigation, the actual science, is figuring out exactly what that something is. Is it fresh magma pushing up from deep in the mantle, entering a reservoir closer to the surface? Is it volcanic gas accumulating faster than it can escape? Or is it superheated groundwater expanding inside what scientists call a hydrothermal system, essentially a vast underground network of steam, hot water, and dissolved minerals, heated by the volcano, but not necessarily connected to fresh magma at all? Here's the twist that makes this genuinely difficult. Magma rising and hot water expanding can produce almost identical uplift patterns on the surface. From orbit or from a GPS station alone, they can look the same. That's exactly why scientists never trust a single signal in isolation. They stack the evidence layer by layer like building a case file. Is the chemistry of the gas escaping from the volcano changing? Is sulfur dioxide output climbing? Has the pattern of small earthquakes shifted in location or frequency? Is heat escaping from the ground faster than it used to? Each answer eliminates certain possibilities and narrows down others. It's less like predicting the future with a crystal ball and more like an entire forensic team methodically working a case. Except the crime scene sits several kilometers beneath solid rock, completely invisible to the naked eye. Earthquakes are one of the most valuable witnesses in this investigation. Every active volcano generates thousands of tiny earthquakes a year, the overwhelming majority too small and too deep for anyone nearby to ever feel. Scientists sort them carefully by type. Some come from brittle rock cracking under stress, others come from fluid moving through underground channels, and still others come from gas forcing its way through narrow fractures. A single earthquake, on its own, tells scientists almost nothing useful. But thousands of them, mapped over months and years, layered on top of deformation data, start to form something close to a three-dimensional picture of exactly what's happening beneath the summit. A picture built entirely without ever drilling a single hole into the mountain itself. Now, to really understand why scientists take all of this so seriously, you need to know what happened just a few hours south of Rainier, back in 1980, at its neighboring volcano, Mount St. Helens. Weeks before that eruption, a massive bulge began forming on the mountain's northern flank. But unlike the slow, gradual inflation being tracked at many volcanoes today, this deformation accelerated violently. Entire sections of the mountainside were measured moving outward by more than a meter every single day, an almost unbelievable rate of change for solid rock. Geologists at the time knew immediately that something extraordinary was forcing its way through the mountain from within. On the morning of May 18, 1980, that unstable, bulging flank finally gave way. Its collapse triggered one of the most powerful volcanic eruptions ever recorded in the continental United States, reshaping the landscape for miles in every direction within minutes. That single event changed the entire field of volcanology forever. It proved, beyond doubt, that carefully watching ground deformation could provide critical warning before a catastrophic eruption. But it also proved something else, something just as important. Not every episode of inflation ends in disaster. Many volcanoes around the world swell measurably for years, sometimes decades, and simply settle back down again without ever erupting at all. That lesson has stuck with volcanologists ever since. Inflation is a warning sign. It is not, by itself, a verdict. So why should any of this matter to you, even if you live thousands of kilometers away from the nearest volcano? Because the real danger from an eruption is rarely just the lava. In 2010, a volcano in Iceland called Eyjafjallajökull erupted. By volcanic standards, a fairly modest event, nowhere near the scale of Mount St. Helens or Rainier's largest historical eruptions. But its ash cloud drifted across much of Europe, grounding more than 100,000 flights over several days, stranding millions of travelers in airports across dozens of countries, and costing the global economy billions of dollars. The lava itself barely touched anyone. The ash touched almost everyone. That's exactly why monitoring a mountain like Rainier isn't just a local concern for the towns nearby. It's a matter of protecting flight paths, water supplies, regional power grids, and coordinated emergency response for an entire stretch of the continent, sometimes depending on wind patterns and ash dispersal for an entire hemisphere. And the tools doing this monitoring today are almost unrecognizable compared to what volcanologists had access to a single generation ago. Artificial intelligence now scans mountains of satellite data continuously, searching for subtle patterns that would take human researchers months to identify manually. Radar can detect ground movement smaller than the width of a coin, across an area the size of an entire city, updated on a regular schedule. Scientists working on different continents can pull the exact same live datasets and compare notes with each other in real time, no matter the time zone. We are no longer simply reacting after eruptions happen. Increasingly, we are learning to read the warning signs that come before them, sometimes weeks or months in advance. So where does all of this leave Mount Rainier? Right now, today, the ground is rising. That part is confirmed, independently verified, and actively tracked by multiple monitoring systems working in parallel. But so far, everything scientists are observing fits a pattern they have documented and studied before, at Rainier and at other volcanoes around the world. Genuine unrest, yes, worth watching closely, but no clear evidence at this stage of an imminent eruption. That distinction matters more than almost anything else in this entire story. A volcano can be genuinely active without erupting. It can inflate measurably without ever exploding. And understanding the difference between those two ideas might be the single most important lesson modern volcanology has learned over the past 50 years. Because here's the truth that no satellite, no matter how advanced, can fully capture. Even with GPS accurate to the millimeter, radar watching continuously from orbit, and artificial intelligence sorting through more data than any human team ever could on their own, the Earth still keeps secrets. It moves when nobody is looking. It builds pressure in complete silence, sometimes for decades at a time. And every so often it reminds us that the ground we casually call solid and permanent is really just a long pause between much bigger events, playing out on a timescale we can barely comprehend. Mount Rainier isn't erupting today, but it isn't standing perfectly still either. And as long as scientists keep watching, every millimeter of ground movement, every small tremor, every trace of gas escaping from deep below, we get a little closer to understanding the mountain that 80,000 people quietly call their backyard, and the immense, patient forces still shaping it right now beneath their feet.